In the previous module, we have discussed several robust regression techniques that we can use to fit into a data set when we have reasons to believe that there are outliers present. In the current module, we will discuss different methods of detecting these outliers so that they can be singled out and removed from the data set or somehow taken care of so that they do not affect our analysis. Let us begin with the discussion of the regression model and the residuals that we can obtain from the model. Let yi be the ith response, xi1, xi2, xip be the observations for ith individual on p explanatory variables, and beta is the vector of regression coefficients beta 1, beta 2, beta p. Then the regression model is given by yi equals xi1 beta 1 plus xi2 beta 2 plus xip beta p plus epsilon I, where epsilon I is the error term. Under the assumption of linear models, the errors are normally distributed with mean 0 and equal variance. That is, variance of epsilon I equals sigma square. Now, the residuals that we can obtain after fitting this model is given by Ri equals yi minus yi hat, where yi is the actual response and yi hat is the estimated response. We can also write the residuals Ri equals yi minus xi beta hat, where beta hat is the vector of estimated regression coefficients. The standard error of the residuals is given by sigma times square root of 1 minus hii, where hii is the ith diagonal element of the hat matrix and sigma is estimated using the root mean square error or MSE from the fitted model. Besides residuals, we also use standardized residuals to single out outliers in a data set. We obtain standardized residuals by dividing the residuals by their standard error. Thus, the standard residuals are given by Ti equals Ri divided by sigma times square root of 1 minus hii. For the purpose of detecting observations that are outliers and influence the regression estimators, more valuable are the studentized residuals rather than the plain residuals. To obtain the studentized residual, we use the formula Ti star equals Ri divided by sigma subscript I square root 1 minus hii, where sigma subscript I is the variance calculated after deleting the ith observation from the dataset. For practical purposes, we estimate sigma by root MSE from the model, and hii as before is the ith diagonal of the hat matrix H. Now, for observations that do not contain outlier, deleting the ith observation does not change the value of sigma square by a large amount. If ith observation is not an outlier, then sigma subscript I square is not very different from sigma square. However, for observations that contain an outlier, deleting the ith observation reduces sigma subscript I square. That is, after deleting the ith observation, the variance sigma square is much lower than sigma square. Hence, Ti square, which is obtained by dividing the residuals by sigma subscript I, will be much larger than Ti or the standardized residual. The studentized residual Ti star follows a t distribution with n minus p minus 1 degrees of freedom. To formally test for outliers, we delete each of the observations one at a time and perform the regression analysis and obtain the test statistic Ti star and test it against a critical value from the t distribution. The t statistic follows a t distribution with n minus p minus 1 degrees of freedom. We can also obtain the corresponding p value and test whether the ith deleted observation is indeed an outlier. For sufficiently large n, we assume that the t-distribution converges to a normal distribution. In case of a normal distribution, the level of significance alpha equals 0.05, the corresponding critical value is 1.96. Hence, we can roughly use the following test criteria. If Ti star is greater than 2, the ith observation is considered as an outlier. Now, as mentioned before, studentized residuals are obtained by dividing the residuals by their standard errors, which is given by sigma times square root of 1 minus hii. The sigma is estimated by root of mean square error or MSE. Sometimes we ignore hii and we simply divide the studentized residuals by root MSE or sigma hat. These are called semi-studentized residuals, and they too are sometimes used to identify outliers. Despite the fact that the studentized residuals help us point out the influential points, not all of them have very large residuals. We would then like to examine the amount of change in the estimate of the parameters and the response in order to single out outliers and not just look at the residuals. Let y subscript I hat be the estimated response and beta subscript I hat be the estimate of the regression parameter after deleting the ith observation. We thus have two new measures of the difference using y subscript I hat and beta subscript I hat. They are called def beta, which is the difference between the estimate beta hat from the entire dataset and the estimate beta subscript I hat, which is obtained by deleting the ith observation from the dataset, and def fit, which gives us the difference between the fitted values from using the entire dataset and from using the dataset after deleting the ith observation. The expression for def beta is given by beta hat minus beta subscript I hat, and the actual expression for def beta in terms of the explanatory variable and the design matrix can be written as x prime x inverse xi times ri divided by 1 minus hii. Now let us derive this expression of def beta. Let x subscript I be a matrix partitioned from x after we delete the ith observation. We see that x prime x can be written as sum over L equals 1 to n xl prime xl. Then x subscript I prime x subscript I can be written as sum over L equals 1 to n xl prime xl, which can also be written as sum over L equals 1 to n L not equals I xl prime xl minus xi prime xi, which equals x prime x minus xi prime xi. Thus, x subscript I prime x subscript I can be written as x prime x minus the ith observation xi prime xi. Therefore, we get x subscript I prime x subscript I whole inverse equals x prime x minus xi prime xi whole inverse, which equals x prime x inverse plus x prime x inverse xi prime xi x prime x whole inverse divided by 1 minus hii. Similarly, x subscript I prime y subscript I can be written as x prime y minus xi yi. Now we know that from the results of linear model, the estimate of the parameters in the regression beta hat equals x prime x whole inverse x prime y. In case of the dataset where ith observation is deleted, we can thus write beta subscript I hat equals x subscript I prime x subscript I whole inverse x subscript I prime y subscript I, which equals beta hat plus x prime x inverse xi prime beta hat divided by 1 minus hii minus x prime x inverse times xi yi minus x prime x inverse xi prime x inverse xi yi over 1 minus hii, which equals beta hat plus x prime x inverse xi prime beta hat divided by 1 minus hii minus x prime x inverse xi yi times 1 plus hii divided by 1 minus hii, because we can write xi prime x inverse xi as hii. Thus, we can write beta subscript I hat equals beta hat plus x prime x inverse xi times xi prime beta hat minus yi divided by 1 minus hi. And from the definition of residuals, we know that xi prime beta hat minus yi is ri, where ri is the residual. Thus, b subscript I hat equals beta hat plus x prime x inverse xi ri divided by 1 minus hii. The vector beta hat minus beta subscript I hat is called def beta. Hence, from the previous expression of beta I hat, def beta can be written as def beta equals beta hat minus beta I hat, which equals x prime x inverse xi times ri divided by 1 minus hii. Now, the other measure that we have talked about is def fit, where def fit is the difference between the estimated response from the entire dataset and the estimated response after we delete the ith observation from the dataset. That is, def fit is yi hat minus y subscript I hat. From the expression of def beta, we can obtain the expression of def fit as follows. Def fit equals yi hat minus y subscript I hat, where yi hat can be written as xi prime beta hat and y subscript I hat can be written as yi prime beta subscript I hat, where we can write def fit equals xi prime times beta hat minus beta subscript I hat, and we have already obtained the expression for beta hat minus beta I hat. So, def fit equals xi prime x inverse xi times ri divided by 1 minus hii, where we replace beta hat minus beta I hat by the expression on the previous slide. And we know that xi prime x inverse xi is hii. Thus, the final expression of def fit can be written as hii times ri divided by 1 minus hii, where ri is the ith residual. Standardized def beta is another measure that is more commonly used than simple def beta. In order to eliminate the effect of units of measurement, standardized versions of def beta are used. The covariance matrix of the vector of parameter estimates beta hat is given by sigma square x prime x inverse. The variance of an individual component beta j hat is given by sigma square times qjj, where we denote qjj by the jth diagonal element of x prime x inverse. It is reasonable to estimate sigma by root mean square error as we have done before, and hence obtain the standardized def beta, which is given by x prime x inverse xi times ri divided by 1 minus HII times square root of MSE times QJJ. Similarly, we can also find standardized def fit. The estimated response is given by y hat equals x times beta hat, and the covariance matrix of y hat is given by sigma square times x prime x inverse x prime. We can write x times x prime x inverse x prime as h, where h is the hat matrix. The estimate of the variance of yi hat is given by MSE times HII. Hence, the standardized def fit is written by square root of HII times RI divided by square root of MSE times 1 minus HII. Now, after we obtain our measures def fit, def beta, or standardized def fit and standardized def beta, a natural question that arises is that how to use these measures to decide which data points are to be marked as outliers. There are several ways of answering this question. If an analyst has firm knowledge of the context in which the data was analyzed, then he would have an idea about which value is too large. The other method is to run down the entire list of measures and identify the ones that are much larger than the other values. A third approach is to use some criteria, such as for def fit, we can use the cutoff of leverage HII less than 2p divided by n, where p is the number of parameters and n is the number of observations in the dataset. A third measure that we use sometimes to detect outliers is Cook's distance. Cook's distance measures the influence of the ith observation on all the yi hats. It is the standardized version of the sum of squares of the difference between the predicted values computed with and without the observation I. The expression for Cook's distance is given by beta hat minus beta subscript I hat prime times x prime x times beta hat minus beta subscript I hat divided by p times MSE. Now, after we have discussed these different measures of detecting outliers, let me illustrate these methods using the life cycle savings data. We will use this dataset to illustrate the use of R to detect outliers. The life savings dataset is an inbuilt dataset in R, so before we fit a model to the dataset, we call upon using the data function, the life cycle savings dataset. The R code used to first fit a regression model is given here. We have used the lm function to fit a regression model to the life cycle savings data. And here the R output is also presented, which contains the estimates of the parameters corresponding to each explanatory variable. We have their standard errors and the corresponding p-values. And the p-values suggest that out of the 4 explanatory variables, population 15, population 75, DPI and DDPI, only population 15 is significant at 0.01 level of significance. In order to find the outliers, we first look at the diagnostic plots. R produces a set of standard plots for the lm function, and these plots help us assess whether our assumptions of linear models are reasonable or not in the current context. In order to plot the dataset, the R code that we use is plot life.lm, where life.lm is our lm function, and the output is given in the form of 4 plots. Now, what are the problems that we may come across while checking the diagnostics after fitting a regression model? The problems are: the errors may not be normally distributed, or they may not have the same variance, or in other words, they might be heteroscedastic. The QQ norm plot, which is the second plot, can help us determine whether these problems exist. When the QQ norm plot is a straight line at a 45-degree angle, we say that these assumptions are met. The unequal variance of errors can be determined by the plot of the explanatory variables x versus the residual. If there is a trend that exists in the plot, then it indicates non-constant variance of the error terms. We can also find outliers from these plots. That is, the points that influence the regression line can be pointed out in the plot of residuals versus leverages in the R output. Now we can use R to plot the residual and the standardized residuals separately. The code that we use is, we use the plot function and we first plot the plain residuals of the lm function life.lm. We can also plot the standardized residuals again using the same plot function on the life.lm. And here we have also presented the R output after using the plot function. Now the studentized residuals may be obtained in R, and then we can test it against the criteria that we have discussed before. After computing the studentized residuals, we can check whether the absolute values of the studentized residuals are greater than 2, then the ith observation is considered an outlier. In R, we can obtain the studentized residual using the following code. If we denote the studentized residuals by R, we can use the studres function to obtain the studentized residuals on the life.lm function that we have used to fit the regression model. We can also obtain def fits using our R code. The R code to obtain the def fits is given here. We can use the df def fits function on life.lm to obtain the def fits. To investigate the observations that have def fits greater than 2 times square root of p over n, where p is the number of parameters in the model and n is the number of observation in the model, will tell us if the corresponding observation is an outlier or not. In the case of the current data set, which is the life cycle savings data set, 2 times square root of p over n equals 0.56. Hence, the observations that have def fit greater than 0.56 should be examined as possible outliers. In addition to def fits and def betas, we can also compute Cook's distance using R. The function that we use in R is Cooks.distance on the life.lm function to obtain the corresponding Cook's distances. There are different opinions about how to use Cook's distance to single out outliers, but the most conservative approach relies on the fact that Cook's distance has an F distribution with p and n minus p degrees of freedom. Hence, we use the critical value from this distribution to determine whether a given observation is an outlier or not. So in this module, we have looked at the different methods of detecting outliers so that they can be singled out and taken care of. We have also illustrated these different methods using example data sets, and there has been extensive use of R to detect outlier from a data set and removed before any statistical analysis is performed on a data set.